All right, well, thanks everybody for joining us this evening. My name is Julie Price. I'm part of the customer engineering team at Google Cloud, and I focus on all of our analytics solutions. But predominantly, I do spend my time in the BigQuery space. One, because I have a data warehousing background that goes back a lot farther than I'm actually willing to tell you. And two, because I think BigQuery is actually the most powerful, most awesome, most amazing thing that we offer in the Google Cloud analytics space. And so this talk today is going to be all about becoming a BigQuery superhero. So give me 1 second, I'll start presenting. And I have to give a little bit of credit where credit is due, and make sure that you know that this theme was borrowed from Felipe Hoffa, who is kind of like the original BigQuery superhero. And you'll see at the end of this, we'll actually give you a link to the blog where he talks a lot about BigQuery superpowers in a little bit different way and gives you lots of different examples of how you can test them out. So Felipe is actually here with us as well, and I'm sure he'll help with answering questions and everything as we go along. So as Joe mentioned, please feel free. I'll do my best to pause and ask for questions. Feel free to ask them directly, or if you prefer to be more quiet about it or can't get it in, type it into the chat. Felipe, maybe you can help answer some of those in real time. Otherwise, we can go back to that at the end of the presentation and we'll get all of those questions answered. And you can see here that you've got mine and Felipe's Twitter handles, so if you are interested in having further conversations, you can always feel free to catch up with us on Twitter. So let's go ahead and get started. So first and foremost, I just want to talk a little bit about what BigQuery is before we talk about how you can start to leverage all of the superpowers that exist in it. So I'll go through this relatively quickly. Just to set the foundation, but BigQuery is the enterprise data warehouse for Google Cloud. It is exabyte scale. We've got many, many customers that have upwards of hundreds of petabytes of data that they are storing and analyzing in BigQuery every single day. And it really is kind of like the crux of a modern data warehouse. And when we talk about modern data warehousing, there's been a long history of data warehouses that have been built based on the technology that was available at the time. And at the time, they did a really good job of answering all those analytic questions, of being able to process certain amounts of data. But data volumes, as you know, have grown exponentially. The velocity with which you have to actually bring in that data and interact with that data has changed. And so we really needed to kind of shift thinking about the way that a data warehouse was actually built and created in order to be able to take advantage of all of this new data that's coming in and all of the different types of data and the speed of data and all that, the typical kind of like 3 Bs of big data. So BigQuery is the answer to that. And BigQuery really kind of goes even beyond your traditional data warehousing. And we're going to talk a bit about the architecture, but at its foundation, BigQuery really is truly serverless. It does not have the concept of big nodes that have storage and computes, many CPUs and lots of RAM attached to them, like some analytic solutions have today. It doesn't even have, when you talk about cloud data warehouses, frequently they talk about this separation of storage and computes, which we will talk about. We do have that, but we take it even a step further from that, because typically in these other kind of cloud data warehouses, you still have these really large nodes that have lots of CPU, lots of computes, and RAM associated with them, and the storage is just kind of separated from that, so that it enables a little bit of scaling separately. But BigQuery is truly built in a serverless nature, such that we kind of grab the CPUs as we need them, we allocate the storage as you load data up, and we'll get into that a lot more completely when we talk about the architecture in a few minutes. But it truly is one of BigQuery's superpowers, is that it is truly serverless, which enables you to elastically scale to whatever your workload, whenever you need to. In addition to supporting your data warehouse with the separated storage and compute and the serverless architecture, it also gives you a whole bunch of capabilities that are not really traditional for data warehousing. So most data warehouses don't really focus on the ability to have real-time analytics, to be able to see data as it's streaming in from various different sources and be able to analyze that in real time. BigQuery does have that capability, and we'll talk about that superpower a little bit coming up. In addition to that, BigQuery also has advanced analytic capabilities. So when we talk about, some of the folks who mentioned that they are in the data science space, most of the time you have to take the data out of the data warehouse to be able to perform these advanced analytic type of functions. And that creates a lot of unnecessary time, a lot of duplication of data that's unnecessary. And so BigQuery has answered that by bringing a lot of that advanced analytic capability actually into the platform. In addition to machine learning, we've got geospatial capabilities. Again, we'll talk about that as well. And another major superpower of BigQuery is the ability to easily share data across, either share your own data to other BigQuery users, but also has an incredible amount of public data sets that are available to you to use that are constantly being updated. So if you think about introducing the concept of bringing weather data alongside your data to be able to analyze that, we've got that type of information. We've got crime information coming from various different cities. We've got all sorts of data around the current state of affairs with things going on with COVID-19 that's constantly being updated so that you can get real up-to-date information. You don't have to go somewhere, pull a download, bring it into your other system, and start to analyze it. It's right there for you, and you can actually analyze that data right alongside of yours, writing queries that join that data together very easily. And then finally, another one of BigQuery's superpowers is really the fact that it's built on the foundation of Google Cloud. And as such, it brings with it all of the security and trust that comes with everything within Google Cloud. All of the data is encrypted, it's sharded, encrypted. The encryption keys are then sharded and encrypted again. So you really have an incredible amount of foundational encryption of the data, both in flight and at rest, and lots of other data governance and things like that that come along with it. I'm not going to focus a lot on that space, so if that's something that you're interested in learning more about, please feel free to reach out. But within an hour or so to speak, we can really only talk about so many superpowers, and that was one of them that I kind of had to leave out of the presentation. So it's just kind of a quick introduction to a lot of the things that BigQuery encompasses. And the reason why BigQuery encompasses all of those things is so that it can eliminate a lot of the frustrations and a lot of the issues that folks have had with traditional data warehouses. So when we think about, as I mentioned, the public data sets, a lot of times when you have to bring in data from various different places, there's really complex ETL pipelines that need to be run. We've got all sorts of things we'll talk about that will enable you to automate your data delivery into BigQuery. Additionally, being able to really make available this data to a much broader audience. A lot of times, your traditional data warehouses, they restrict to only a few users. Ad hoc usage tends to get pretty limited. So what ends up happening is that people end up extracting data and moving it into other systems so that they can operate on it. And we don't want that to happen anymore. We don't want people to have to create these copies of data and silos of data. So we've done everything that we can to essentially make all of those insights accessible and available so that we can scale as we need to for the users that you want to introduce to this data and not have to limit what folks can do in the system. Additionally, traditional data warehouses tend to be optimized more for legacy business intelligence. And that's great because those types of things really need to continue to happen. But where things are really going is becoming the foundation for machine learning, for AI type of workloads. And so we want to make sure that we have the best solution and the best foundation for that possible for you. And so it's optimized really to be that foundation. I mentioned the ability to do real-time insights, talked a little bit about data governance. And one of the really huge superpowers of BigQuery is that because of the serverless nature of it, and because it is a managed service, you no longer really have to worry about the typical things that a lot of folks have to worry about along the terms of, what happens when I have to patch my servers? What happens when I need to upgrade things? What happens if I have hardware that's going out of support or hardware that's getting old and I want to upgrade it? All of those types of things are managed and taken care of for you with BigQuery. And so you really can simplify your data operations and allow those folks to focus on things that are going to be really impactful, like making sure that people are getting the best performance out of the system and making sure that all of the insights that folks want to get, they're able to get. So those are kind of the reasons why BigQuery was created and a lot of the advantages of BigQuery as a modern data warehouse, and we'll drill into some of these as we go on. Pausing, any initial questions?
I had a question about the public data sets.
Sure.
Are they versioned? Like, are they kept kind of static or?
So it depends on the data set and who owns it. Whoever owns the data set is kind of responsible for how and when it gets updated and refreshed, and whether or not it gets snapshots or if it's constantly dynamic and changing.
Okay, but that's like transparent, somebody could see.
So if you go into the console and you look up, I can show you when I get into kind of demoing a little bit, I can show you really quickly. When you go in, search for a public data set, the owner of the public data set gives you a bunch of information about it. So you should be able to see it right there.
Okay, thank you.
Sure thing. All right, so moving forward, I wanted to talk a little bit about the architecture of BigQuery. I'll go through this relatively quickly because there's lots to get to. But as I mentioned, we do have this complete separation of storage and compute. That really offers you the ability to scale each one completely independently of each other. So let's say today you decide, I've got 50 terabytes of data and I want to load it up into BigQuery. You go ahead, you trigger a load job, you load this 50 terabytes of data, we allocate the storage blocks to you, and that's it. You don't have to do anything, you don't have to tell us about it. If you want to load 250 petabytes of data, it might be to your advantage to let us know before you do something like that. But the reality is of BigQuery that as you load data, we're going to allocate the storage blocks to you. And it's not until you actually query the data that we ever allocate any type of compute resources for you. So they're completely separate from each other, and the compute resources are allocated at the time of the query. So when you send a query into BigQuery, the query execution engine takes a look at it and says, how much compute do I actually need to operate each stage of this query? And that's a really important thing to note, that it's stage by stage. It doesn't look at the query as a whole necessarily. But it'll say, the first stage of pulling the data from, from storage and filtering the data, how much compute do we need? Once I've done that, then to perform any calculations, aggregations on it. And at the time of each stage, it's going to pull the compute that's needed. And when that stage is completed, it's going to release it back into the wild. So essentially, this gives you that elasticity to grow up and grow down as needed as your workloads are operating. Now, this is all running in Google's data centers. It's all operating on Google's petabit network. So when we talk about kind of the I/O between storage and compute resources, you're getting highly optimized, a highly optimized process. And there's also this distributed memory shuffle tier that's core to the BigQuery service. And essentially what that does is it stores all of the information in between stages of the query, so that if anything was to happen, this is what we talk about, something strange happens with a compute node and we actually need to swap it out for another one, that's no big deal, not a problem at all. Something else that we often do is we might run a stage twice at the same time in different ways to see which one gets it done faster. And so again, that's where kind of the shuffle tier comes in really handy, and we can do that. So that's kind of like the foundation of the way that BigQuery operates and the way that we allow you to kind of elastically scale your storage and your your computes completely separate from each other. Now we'll talk a lot more about getting data into the system, so I'm not going to dwell on that for too long. But we do have both streaming ingest and bulk loading. Bulk loading is free, so if you've got your flat files, if you've got your data in a variety of different formats, which I'll talk about, you load that up into BigQuery. The actual act of loading the data, it's using compute resources, obviously, we just don't charge you for them. And that's the beauty of having a managed service, is that we can throw all of these resources at it for free for you so that you don't have to worry about that. So we have that free bulk loading, we have the streaming ingest, and on the consumption side, so as you're trying to consume the data, you want to run queries, you want to build applications on top of it. It is SQL 2011 compliant. So I think one of the key things sometimes I forget to say about BigQuery, because it's so native to my brain, is that although it doesn't necessarily look like a database under the covers, a traditional database, it's a database. It's SQL compliant. You've got tables, they've got columns and rows. You interact with them in the same way that you would any other database type of environment. In addition to that, there's a REST API, a web UI and command line, ODBC and JDBC connectors that we actually work really closely with a company called Magnitude, who actually creates those for us. And then client libraries in 7 different languages. So you can build an application pretty much however you want, an analytic application off of BigQuery, and it's completely open for you to leverage in whatever way you see fit. Okay, so I want to talk very, very quickly about the managed storage. So the tables are stored in optimized columnar format. We store the tables in, it's called capacitor format. It is proprietary for BigQuery, so only BigQuery, in effect, only BigQuery understands it, but it's optimized for BigQuery processing. Each table does get compressed. It gets encrypted on disk, so we're compressing it both, to save space, but also so we can operate on compressed data, which creates some efficiencies as well. Now the storage, we get 11 nines plus of durability, because we essentially replicate across various different data centers every single table that you store. And of course, it does support that streaming ingestion that I was talking about. Now, one of BigQuery's other really amazing superpowers is its ability to do time travel. So the way that storage works is that every time you make a change to the table, we actually create what's called a new storage set of that table. And over the course of 7 days, we will maintain all of those storage sets. So you can easily write a query that says, select these fields from this table for system time as of, and whatever that timestamp is that you're interested in. So this is really powerful. This works even for deleted tables. It works even for tables that have the same name but have changed. So you can get back data that you've accidentally deleted. You can get back to a state that you were in previously. Or let's say you are running some advanced analytics capabilities and you want to make sure that your data, that the data, that sample that you're using never changes, but you realize maybe you needed another feature, you needed to bring in additional data or change the filters, but you want it to be as of a certain point in time. You don't have to take a snapshot of that table. As long as it's within the last 7 days, you can just use this for system time as of in your query, and it'll give you the data exactly as of that timestamp. One tricky, annoying thing is that you cannot say where timestamp subtraction is current timestamp minus 7 days, because by the time the query actually makes it to the system, it's going to be greater than 7 days. So you have to do, 6 days, 24 hours, 59 minutes, and 59 seconds. But I'd like to see that changed at some point in time. So time travel, really big superpower of BigQuery, and something that I think is really important to mention. Another superpower is BigQuery's remote memory shuffle. So for those of you who are familiar with distributed data processing and distributed storage, you know that bringing data together, from distributed storage, performing any type of complex calculations, any type of things where you might actually need to bring all like data together in order to do things like do a count or a max, a min, any type of aggregations, joins and things like that. You need to be able to move data between workers, because our workers are actually very small. We don't have Like for example, in a Hadoop world, you might have, you know, a half a terabyte of RAM on a node to use. What we're talking about are units of computer called slots. And when we talk about slots, they're teeny tiny. We're talking about, you know, half of a vCPU and a half a gig of RAM. So when we want to actually perform, say, accounts, where we're looking at, you know, all of a particular table that has data by state, if we wanted to count the rows by state, we need to get all data for a certain state on the same worker, essentially, to be able to come up with that count number. And so the in-memory shuffle tier really helps with that because it enables us to take the work that has been done to date, shuffle it, and make sure that all of the like things end up on the same worker. And it's all done in memory. It's highly optimized. And this shuffle tier also stores all of that state between stages to make sure that if something happens and a worker goes down or the query needs to be paused for some reason, we can always get back to where we were previously. So it enables really incredible capability for this distributed processing, scalability for this distributed processing, and the ability to essentially run all of the analytics across incredibly large volumes of data in a really efficient way. All right, so I want to talk now about getting data into the system, but I'll pause again to see are there any questions that that anybody wanted to answer imminently that can't wait.
Julie, I think there were a couple that popped up in chat.
Okay, let's have a look. Okay, so it looks like Felipe's been answering most of them. However, I'll kind of quickly review in case people aren't tracking it. So one of the questions is how does pricing work for streaming ingest? And it's actually, and I don't remember the numbers off, 5 cents per gig, I believe, is the streaming pricing. So the reason for that is because we're using additional compute resources as we're bringing that in. And so that's just for streaming data, that meaning like I want that data to be available in real time. Any type of bulk loads, as Felipe mentions in the chat, are completely free. So what ends up happening is like if you wanted to load the data every hour, every 15 minutes or something to that effect, that's going to be completely free. But if you truly want that up to date, you're going to have that pricing of, I think it's 5 cents per gig. Question about changing the time travel to more than 7 days. Right now, that cannot be changed. So 7 days is kind of a hard-coded thing. It's always worthwhile if you're interested in having longer than 7 days. If you are working with BigQuery, you have contacts at Google, it's always worthwhile to raise that. Again, feature requests coming from outside get good attention, and so we're always happy to listen if you have these cases where you need more than that. And Felipe makes a very important note there that you do not get charged for that look-back amount, which I think is really, really important, because if you think about constantly changing data on a really large table, that could be a substantial amount of storage that you don't have to worry about paying for. Clarification on memory shuffle, is it automatic or something to tune? It is automatic, so it's part of the service. It's not something that you can tune. However, understanding your data, the skewness of your data, and how you're querying can impact the amount of data that gets shuffled. So there are some best practices around that I don't have time to go into today, but for the most part, it is completely under the cover thing that you're not going to have much impact on. And then how does BigQuery get consensus among nodes for committing data? What kind of serialization guarantees are there? So, under the covers, I guess when you're talking about committing data, are you thinking, Dylan, of multiple people are writing to a table at the same time? Are you thinking of how I was talking about that a query might have the same stage being processed twice to see which comes back faster?
Multiple things writing to a table at once.
So all writes to BigQuery are atomic in nature, and so what's going to happen is if you're writing, anytime that you're writing, if there's people querying, if your write has not yet committed, they're going to see everything pre-commit. If multiple people are trying to commit to the table at the same time, they're going to essentially be serialized based on when they started. If we're talking about processing using data manipulation language, so you're writing, you're doing an update or a delete or something to that effect, that might affect it might affect rows that were previously inserted into the table. They will be queued based on the time at which the query was, the DML query was actually issued.
Are there any sorts of locks?
There are no locks.
Okay.
Alrighty. Okay, so we're going to go on to getting data into the system. I keep on being on the wrong screen when I try to forward my slides, so it doesn't work. So we have a number of different data ingestion options. So first we have batch ingestion. You can write data from GCS, or you can use HTTP post, so using API. There's multiple file formats that are supported. I'll show you a slide on that in just a second. As I mentioned, inserts are atomic, so it is not going to say like batch up. Say you load 1 million records, it's not going to batch up 100,000 at a time and kind of be serialized. All data arrives at once. It's all or nothing. If there's a failure at the very last row of processing, that's going to cause a failure. You do have the ability to set max bad rows. So like say you're loading something up and you wanted to say, I'm okay with, with 50 rows being bad, meaning, there's some type of data type error or whatever it may be. You can set that type of tolerance and actually ignore those bad rows and not have it fail. Additionally, you can do streaming ingestion. So our streaming ingestion is really interesting because it's immediately available from the buffer. Now, those of you who are familiar with columnar storage know that actually, writing one row at a time to columnar storage is actually a very costly effort. And so essentially the architecture is set that it has a buffer to collect those rows as they come in. And when you're querying against a table that has streaming inserts turned on, you'll actually query against the buffer and the data that's all organized in a columnar fashion. And eventually there's a buffer flush that happens that reorganizes the entire table into the columnar storage. The streaming ingestion does have the capabilities of streaming 1 million rows per second or up to 1 gig per second, which is pretty spectacular. In addition to these two options, which we already talked about, you can also do query materialization. So of course you can materialize results of a query from other tables. You can use various different ETL solutions to be able to do this. And you can also use query federation. So another kind of superpower of BigQuery is the ability to pull data from other places, create federated tables or external tables, and write a query against that. And then you can materialize the results into BigQuery storage. And then finally, BigQuery Data Transfer Service, another pretty great superpower, enables you to manage ingestion of other sources. So if you think about a lot of like the Google Ads data, DoubleClick and things like that, but also things like Teradata and Amazon Redshift and S3. And what's great about these things is that it will actually understand what the schema is of the source table. It'll create the corresponding schema and do all of that translation into BigQuery. And then you determine the frequency with which you want that transfer to actually occur. And it'll manage that transfer for you. So now you cut out the ETL kind of middleman or middleware, and you don't have to worry about all of the different difficulties around doing schema translation and all those types of things. And of course, there's third-party integrations as well. So drilling into these or summarizing that quickly, and I'll drill into a little bit more. Batch ingest is free. It is always free for you. It does not consume query capacity. So your users are querying and they're using all of the resources that they need. it does not consume that capacity at all. Because of the asset semantics of the data loads, again, users continue to query. They never have to worry about getting dirty data or dirty reads. You can load petabytes of data a day. We have customers who actually have loaded petabytes of data. I think we don't have any that are consistently loading petabytes of data per day, but I could actually be wrong on that. And then streaming API for real time, again, up to 1 million rows per second, up to 1 gig per second of actual streaming data in from wherever you need to stream it. I mentioned the different ingestion formats, and so this is one of those best practices that if you want to optimize your data loads, the various different formats or serializations that are available to you, Avro, both compressed block, Avro, and uncompressed, Parquet and RRC, CSV, JSON, compressed CSV, and compressed JSON. So kind of a key thing here is that when we look at compressing like a CSV or a JSON file, we are not able to parallelize the loading of that data because we have to uncompress it. And so that's really the slowest way. It may be the fastest way to get it into Google Cloud Storage, but it will be the slowest way to get it into BigQuery. The fastest way is going to be compressed block Avro, and we've actually seen that deflate is actually faster than snappy. So if you really want the absolute fastest data loads, I would recommend going with deflate compressed Avro. So the data transfer service, as I mentioned, it simplifies that batch ingestion for certain data sources. So we've got a bunch of managed data source providers. You might recognize that they are pretty much all on the Google side, on the Google Ad side. So obviously we know a lot about these data sources. So this is really big for different marketing data. If you're leveraging these tools, you can essentially with a few clicks be able to get all of this data into BigQuery so that you can query it alongside of all of your other data. But you can also use data transfer service to set up your ingestion from Google Cloud Storage. So it'll automatically ingest those files. You can set up a regular schedule to do that. Amazon Redshift and S3 and Teradata I mentioned, this is pretty big, if you are doing a migration from one of these, or you're kind of running in parallel as you're doing a migration off of, say, Teradata to BigQuery, and you want to just bring data in incrementally every day to run certain workloads in parallel, you can do that. And then scheduling queries. So you can schedule queries to generate new tables from BigQuery queries. And you can do this on a regular schedule. So let's say you had tables that you wanted to refresh nightly for dashboards that your CEO might be looking at every day. You can use the scheduled query capability to do that. And there are a lot of third-party data sources out on the marketplace. So if you have a third-party data source that you wanted to use for the transfer service I recommend going and typing it into Cloud Console Marketplace and seeing if it exists, because there's a good chance that it does. And lots of partners who we work with for data ingestion as well. So, and I think we'll give you these slides so you can kind of drill into this, and it's all on out on cloud.google.com as well. So that's it for ingestion. I want to talk about data modeling a little bit, but again, we'll pause. I know there were questions in the chat, and I'm not sure if Felipe's been kind of answering all of this. Let's see. So in case of bulk loading files from GCS into BigQuery, there is sort of file history tracking that helps avoid loading the same file twice. So every time you run a load, there is something that gets logged. So technically you could look at the logs to do that, but there's not anything that I'm aware of that would kind of automatically say, hey, you already loaded this file, if that's the kind of thing that you're looking for. Also, I know folks sometimes have asked for, to have the file from which an element of data was loaded as kind of a piece of, like an attribute of a row, and that's not something that we have either. So federation is currently limited to sources that sit within Google Cloud. So PostgreSDB on like AWS RDS is not available, but Cloud SQL, Postgres on Cloud SQL is available for federation. So continuing, it looks like Felipe, you're answering lots of questions here. So that was the last one on data loading. I want to talk about data modeling, but I realized that I also wanted to do a little bit of demoing so that I'm not just showing you slides. So maybe I could just do a quick demo to show you BigQuery in general and to show you, how fast actually BigQuery can operate. So this is a BigQuery UI for those of you that aren't familiar with it. You have all of your navigation on the left-hand side, your query pane on the right, and information about whatever it is you're currently doing in this panel here. And so you can see kind of the history. I haven't actually run any queries in this, as this particular user in this project previously. So we're going to be the first ones to do it right now. But I have some data on GitHub now. I've got lots of other data over here, but I wanted to be able to show you just specifically my GitHub data. So I can filter everything out. And we're going to take a look at data and really we want to see how many hello world GitHub entries do we have using Golang to create that, right? So that's what the query is that we're looking at. And we have two tables here. We have a contents table, which has a pretty simple schema of the GitHub content information. And if we take a look, it's about 2.25 terabytes large. So that's the amount of data. Now you have the ability to preview here. This is definitely a best practice because when you preview, you can get information about the data that's sitting in the table without expending any type of query resources. And so I know a lot of folks are used to doing select star against tables, and we don't really want people to be doing that. So doing preview actually is kind of a storage operation. It's just visually displaying some information from storage. And if you're so inclined and have the time, you can actually go through every single page and look at every single row in the table and still get to see it. And this table has 263 million rows in it. So we've got 2.25 terabytes of data, and here, and we're joining with another smaller table, about 320 gigs, that has information about actually the file paths and everything. So you can go ahead and run this query. While you're running it, it's going to give you information about the query stages, as I mentioned, and we can kind of monitor that as we go. So you can see what type of information, like is there any wait time, where is the time essentially being spent? And of course, it looks like it's not fully updating in real time at the moment. But you can also see what each stage is doing. So let me just go back over that quickly and finish the thought. You can see in stage 1, we're actually reading data from the files table and we're filtering it. And then we're passing that out to stage 1 output, which then might be used here. We're coalescing the data from the stage 1 output in order to then perform additional functions on it. So in here, we're trying to do a count distinct. So we need to understand, how many, we need to do various different aggregations against that table. And then we need to join information together. So you can see exactly how much wait time, how much read time, compute time, and write time is spent. You can see how many bytes are shuffled. So this is a good way to know if a query maybe is not performing optimally, if the byte shuffled is really large. And particularly if bytes spilled to disk is greater than 0, that means that essentially you're overwhelming the amount of RAM that we're making available for shuffle, and therefore we're spilling to disk, and obviously that's going to create some performance issues. Now the query itself took 20 seconds to run, but it used 3 hours of compute time, actually almost 4 hours of compute time. So that's kind of the level of parallelism that we're achieving because we are throwing X number of slots at the problem in order to get it done in 20 seconds. The way the BigQuery works really quickly from a resource allocation perspective is that if your query is the only query that's running in the system, we're going to figure out how many slots are needed for each stage, and we're going to give you those slots. When other workloads start becoming active, We essentially do fair scheduling of compute resources. So if it's a very active system, this particular query might have the same slot time consumed, but the elapsed time may be longer, because ultimately we may be giving less slots, which means less levels of parallelism to each stage of the query, because we want to make sure that the other workloads that are running are getting their fair share of the compute resources as well. And because it is a multi-tenant system, we do kind of, when the systems are very active, we put limits around how many slots are available, unless you decide that you wanted to purchase a guaranteed amount of slots, and then we will always guarantee that you have those slots available. That's a longer conversation for another day, but I just wanted to mention that. But so essentially, we processed through 2.5 terabytes of data in 20 seconds. Not too bad. And we got our results back, our discount distinct of the hello world repos for Golang. So just a quick kind of introduction to the BigQuery world. I'll go back to presenting for another couple of minutes, and then we'll come back out over here to take a look at some other demos. And I think probably another like 30 minutes for presenting. Is that right, Joe? Before we want to spend more time with like Q&A and networking?
Yeah, exactly. So,
okay.
Yeah.
So I'm gonna put my East Coast talk or my East Coast voice on and talk faster. Okay, so schema design in a nutshell. I want you all, if you remember nothing else from this discussion, although I hope you remember lots of other things too, but if you remember nothing else from this discussion, I want you to remember that with BigQuery, denormalization is not a requirement. And I say that because there's a lot of folks who are kind of spreading around that in order to make BigQuery work, you have to denormalize your data. And that is absolutely not true. It was true at one point in time that you're not going to get very good performance, you would not get optimal performance. That is no longer the case. Our engineers have done incredible work to ensure that you can bring your star schemas, your snowflake schemas to BigQuery and have them run in optimal fashion. Now, there may be scenarios where denormalization might speed things up because it would reduce the amount of data to shuffle when you're joining tables together. And so you may kind of take the approach of bring your data model as it is. Like, let's say you're migrating your data warehouse, right? Bring your data model as it is. Test things out, and only where you see performance issues, then take a look at maybe optimizing things. But the reality is that if you try to optimize in the beginning, you're probably not always going to get it right, and we're probably maybe going to do it better with your original data model, and so let's not have that happen. One key thing, though, is that you do always want to partition and cluster your larger tables by fields that are frequently filtered on. I'm going to drill into partitioning and clustering in just a minute, because these are really important concepts in BigQuery. BigQuery does not have your traditional indexes and traditional statistics and other things that are used for performance tuning. The way that you have control over performance tuning is partitioning and clustering. That's kind of like the #1 thing that you're going to do to optimize your performance. You also want to take full advantage of nested and repeated fields and denormalized tables if your data naturally falls that way. So if your data is coming in nested JSON and you wanted to not have to unnest it to create a flat table, then it might make sense to make use of nested or repeated fields, because this is actually another superpower of BigQuery, that we can operate with that type of data. And so as I mentioned, in a nutshell, optimize to solve actual problems, not expected problems. Bring your data model as it currently sits. If you're migrating, give it a try. And if things aren't performing optimally, then we can look at optimizing. So now, design pattern for partitioning and clustering. Like this, again, #1 thing that you're going to want to think about. So partitioning. Partitioning is actually creating physical partitions of your data. So it will create different files for each partition, and it can, like partitioning in pretty much any other database system, it can dramatically reduce the amount of table that needs to be scanned provided that you leverage those partitions and filters. So there's a couple of different ways that you can partition your data. There's ingestion time partitioning. So it's just going to append a pseudo column to every single row at the time at which it was ingested. And so that's really good for any type of like streaming or weblogs and things like that, where like you're probably looking at the last so many hours of actual data that came in. However, you also can do time partitioning based on a user date or time column. And this is really good for, you know, more traditional data warehouse type of things where you have a field, right? You've got like your transaction date or something like that in your table, and you frequently filter on that. So partitioning on that actual date works really nicely. And what happens is when you load the data up, we read what's in that date column and say, okay, it belongs in this partition. So it automatically creates each partition for you. And then you can kind of add and drop partitions, you know, very easily that way. And finally, integer range partitioning. So this enables you to have any type of an integer field. So if you've got different IDs, like store ID or something to that effect, and you wanted, you know your data and you wanted to say like 0 to 9 goes in this partition, 10 to 19 goes in this partition, you can define what your integer ranges are. Anything that falls outside of, say, the partitions that you define will go into like an unpartitioned partition, so to speak. And anything that has a null value in the column in the table goes into a null partition, right? Because it doesn't kind of fall into that category. So you never lose data if they fall outside of those partitions, but you have more control over, you know, how your partitions are set. The key with partitioning is that we want to think about, first of all, it's going to be a single column, and we want to think about the fact that we don't want to overwhelm the system with a whole bunch of really tiny partitions, because that is going to have the opposite effect of performance gains at that point, especially when you do have scenarios where you don't want to filter on that partition column, because now we have to string together more files than we would if you didn't create all these little partitions. So we're really looking at a sweet spot of around up to 4,000 partitions. You don't want them to be too small. And you don't want to have 4,000 partitions that each have one row in it. That's really unnecessary. So you really kind of want to look at tables that are a little bit larger, where the partitions might be somewhat evenly spread, although that's not really necessary. But again, not too many more than 4,000 partitions. We can increase that number given the right use case. So, but you know, 4,000 is kind of a sweet spot. Now, clustering, what clustering ultimately does is it optimizes the way that the data gets stored within the partitions, or you don't necessarily have to have a partition, but ultimately you define what your cluster keys or cluster fields are. You can have up to 4 columns. It can be completely diverse. It doesn't have to be time or integer. And the key thing here is that when you create it, your cluster key, you basically are saying, I want my data. It's like the same thing as, say, ordering the results of a query. If you cluster by 4 different columns, it's going to first order results by the first and outermost. Then it's going to order by the next, then the next, then the next. So you're creating like clusters within clusters of each level of your cluster fields. Ideally, you're always filtering on the outermost field, ideally, right? Because that is going to enable us to take a look and say, we know essentially like where these blocks exist within the partitions, and we have the capability to stop scanning a lot earlier if we're filtering on cluster fields. So you get a lot of performance benefit from this as well. And also, we didn't talk about how BigQuery is the cost structure is, but one cost structure of BigQuery charges you for the amount of data that's scanned. So if you leverage partitioning and clustering and you scan a lot less data, you'll pay a lot less money for actually operating in BigQuery world. So I want to show you an example of this really quickly. You can see my dog's head peeking out over there. So I have a table, a sales partition table. This table is a petabyte. It's got 1 trillion rows in it. It's a lot of data. Let's say I wanted to see the total sales by day. I would have to sift through a petabyte of data. Now, I didn't mention here that we have this kind of query validator that happens whenever you write a query up here, and you can see I have a petabyte of data, but actually this query is only going to process 271.9 gig when run. And that's because I've partitioned on this order date field, this order date field, and I'm filtering on it. Now you can see if I change and say, actually just give me a couple days worth of data, now we're down to 16 gigabytes of data. So we know that we're only going to process maximum 16 gig of data. But let's go back to January 1st. So now a petabyte table with 1 trillion rows, and I can go ahead and run this query, and we'll see it comes back in just a few seconds. It's pretty spectacular. We can summarize this data for the month, order the results. 5.6 seconds it took, actually, to run that. And if we look at execution, slot time, 1 hour and 39 minutes, not too bad. We were able to parallelize that quite a bit. We get these results back incredibly fast. But one other thing that I want you to notice is that this query will process 271.9 gigabytes when run. Actually, it only processed 326 megabytes. So again, if you are on that on-demand model where you're paying for the amount of data that gets scanned, we've just taken what would have been a 1 petabyte scan of data and pared it down to 326 megabytes of data. We were able to do that in 5.6 seconds by partitioning, by filtering on a partition field. And it turns out that customer key is one of my cluster fields. And so because the data is then ordered within the partitions by customer key, we can much more easily identify where in the blocks that cluster actually exists and stop scanning when necessary. So I personally, I've worked on SQL Server and Oracle and SAP HANA and all these other solutions. And that every time I run that query, it makes me happy. Because none of those others could actually do that. So now, clustering is interesting because your data is going to get out of sort as you add new data in. So you're going to need to recluster your data. That's fine. BigQuery does it for you. It does it for free. It doesn't consume any query resources. It's completely autonomous. You never have to worry about it. So like Ron Popeil says, set it and forget it. Define your cluster columns, and we'll take care of the rest for you, and we'll make sure that it's always optimized for you under the covers. So that was a lot all at once. I know we only have 15 or so minutes left, but do we have any questions on partitioning and clustering? Check the chat. It looks like it's been quiet.
Does it offer a way to analyze the data set and offer suggestions on how things should be partitioned?
I would love that. And I think that is something that folks have talked about having like a recommender, but no, it does not exist today. Repartitioning, I saw that pop up and I saw Felipe just answer, but repartitioning, essentially, you know, your partition, when you define your partition, it automatically is repartitioning for you as your data gets loaded, right? It's always going to essentially partition the data for you. So, okay. So, right. But as Felipe was saying, yeah, like if you do it as a query, it will not be free. Like if you do a select star, you know, into a table with a different partition reference, that will not be free. If you take the data from cloud storage, create a new table schema with a different partition, and you bulk load into that table, that operation is free. It looks like Felipe was typing at the same time I was talking, so. Alrighty, other things, I think somebody said they wanted to learn more about something. Nested and repeated fields, okay. So just really quickly here, nested and repeated columns, I don't think I set up a demo for this, but essentially you can have both nested and repeated fields in BigQuery, and I can show you a bit of this rather than talking about it. So this table trigrams has nested and repeated data in it. essentially, if we take a look at the schema here, each of these is a first level column. Anytime that you see this dot kind of notation here, that means that we're getting into a repeated field, meaning that you can have more wide, so you can have more than one value. So it's an array, but it's a single row array for each. And then you have the ability to also have a record or a struct type, which could have both more than one column and multiple rows of data. So if we do a quick preview here, we can see exactly what we're talking about. So we have, our single row here, our cell value. We have multiple actual records for the cell value in here. I don't think I have any saved queries written for this, but essentially you have the ability to query anything that is kind of a top level row. You can do certain aggregations for any of like those top level columns. So let's say actually if we look at our sales data, this is a really common scenario. Our sales data, preview takes a second here because of the amount of data. But our sales, it's typical, you've got your sales order key, your order date customer key, and you've got all of your line items. Well, frequently with your sales order, you also have the total sale, the type of currency, maybe you have the number of items that were sold. So if I wanted to just see like what were my total sales, I could just add this total sale column. But if I wanted to see then also like show me the count of the number of sales that have a particular product in it, it's very easy to query this table and be able to see that as well. And so you get a lot of benefits from being able to query this kind of natively. And you can also then unnest this data to create a more flattened structure of it, to query and operate on it in a more of a traditional tabular format. If I go through the rest of the presentation and then we start chatting at the end, I can come back and give you a quick demo of like how you can query and unnest, but I just don't have that all that stuff saved, and I don't want to watch you. I don't want to have you watch me muscle through like writing the query from scratch at the moment. But we can come back to that. So you can essentially, like, it gives you that more natural representation of that hierarchical data. It is much easier when loading this data from JSON or Avro files. Now, I would say if you have this data already kind of in a normalized fashion, coming from wherever it's coming from, I don't necessarily recommend you going through and changing it all to nested unnecessarily. But if your data lives in nested, naturally in nested format, definitely I would take advantage of this type of data model. Okie doke. So we have some questions here. It looks like maybe Matthew's been answering them. I want to make sure that we get through a little bit more of the content to get to some of the coolest superpowers that we have in BigQuery. So I'm going to go through that, and then we can come back and answer questions as well. So when we talk about analyzing data, as you can see, you can analyze data the same way that you do in any type of SQL platform. There are some best practices around querying, like don't run a select star across 1,000 column table if you only need 2 columns, because it's going to be a lot faster in columnar format to just pull the 2 columns that you need. Select star is not going to have the best performance, and it's going to be pulling back a bunch of unnecessary data. So there's things like that. But generally speaking, you query it like any other kind of tabular backend. But one of the key things that I think is important to recognize is that because BigQuery is columnar, because BigQuery operates on these immutable storage sets in the back end of the data, there are some best practices around DML. So first of all, DML operations, they are completely unlimited. You can run as many of them as you want in a day. However, they will be queued up. They will be serialized because we don't want to create any competing scenarios where multiple things are trying to update the same row at once, right? So we need to make sure that that gets serialized. It is absolutely a best practice to batch up your insert statements, to batch up your update statements, using merge statements to do update, insert, and delete all at once. These are best practices. So like, I know coming from like a Teradata world, a lot of times you might be inserting rapid fire one row at a time in a more transactional type of nature. That is not going to operate as well in BigQuery space. So it's easy enough to kind of batch those up into a single insert statement that's inserting thousands of rows at once. That's going to be great. But if you try to do one at a time and throw 1,000 inserts in a second at BigQuery, it's not going to operate the same way that Teradata does, because it's just different architecture. Using a staging table is sometimes really good to do, to like kind of quickly track changes to rows. So if you have keys on your row and you know you want to perform an update, instead of actually performing one single update, you can kind of use a staging table to maintain how a table is changing throughout the day, and then use a merge statement kind of at the end of the day or on a regular basis to actually merge that into a final view of the table. And then you can have a view that looks at the current table and the staging table together in order to do that. So kind of when you're thinking about your traditional like dimensional updates and things like that that are happening in a data warehouse on a regular basis, using that staging table, then making the comparison and using the merge statement is definitely a best practice there. Now, queries get cached per user. So that's actually great. Leveraging the query caching is fantastic. So that query that I just ran over here that took 5.6 seconds, if I run it again, it's going to take essentially 0 seconds. And that's because we have cached data. So as long as the query doesn't change and the data doesn't change, lose my screens, you can operate on cached data, which is fantastic. Doing any type of like non-deterministic functions prevent caching, right? So like if you do current dates, time, or now, that changes every second. So we're not going to be able to cache those results. Either the entire query and its results are cached or none of it. And caching gets invalidated when the data in the table changes. Something not listed here is a query cache is essentially 24 hours. So even if the data does not change in the underlying table, after 24 hours, we're going to eliminate that. And that's ultimately because what we're doing is storing we're physically materializing the results of the query, and that's what becomes the query cache. And so we're not going to keep that around forever. So, 24 hours later, you run the same query, it's going to actually use compute resources again. Materialized views are something that is really fantastic if you have certain types of queries and certain types of aggregate functions that, that you want to leverage all the time. And you want them to essentially be able to stay in sync with the backend table. You can create a materialized view. Currently, these are limited to single tables and certain types of aggregate functions. So like an average doesn't qualify here because an average has to scan the whole table all the time. But counts and sums and things like that, you can do. And what happens is it kind of caches the results of the aggregation, and it recognizes when was the last time the view was materialized, and are there any changes that have happened to the table since then? So if needed, it can go against the materialized view and the backend table to pull any additional new data. And then on a regular basis, the materialized view gets put into sync with the table. You don't have to manage any of that. All you have to do is create the materialized view, and from that point forward, it's essentially optimized. Now, another really, really cool thing that we have is the BigQuery BI engine. And this is it's essentially an in-memory cache and OLAP analytic engine that exists within BigQuery. You can turn it on and say, I want to leverage X gigs of BI engine against your data, and it's essentially going to be smart around the way which data essentially gets cached into memory. And it's going to give you that sub-second reporting. So this is really good for those BI use cases. Currently, it is dependent on Data Studio, but it is coming soon as an API for partner BI tools to use. So essentially, it's giving you that kind of super fast reporting, super high levels of concurrency. The user caching, like we don't have to worry about that anymore for use cases that leverage BigQuery BI engine. So that is a very, very cool thing. Now, that's it for the analytics section. I have a couple of other things if we can go a few minutes early over, because these are some of the superpowers that are like truly differentiating for BigQuery, and I think make a huge difference in the BigQuery and in the analytics space. So, were there any questions on the analysis piece though that haven't been answered? I guess. Reading through the questions, I'm going to let Felipe and Matthew. It seems like you've been answering some of the questions that are a bit longer. I'm going to let you continue to do that in the chat, and we can circle back to it after completing these sections. So very quickly, BigQuery has this capability of BigQuery machine learning, BigQuery ML. So BigQuery can actually be the source of structured data for training your ML models. And that statement could be said for any data warehouse, right? However, what BQML enables you to actually do is to create your model off of that data using SQL. So not only can you just use SQL to actually write the creation of the model and determine from historical data, like which is your label field, what type of model do you want to run, then you can actually use SQL once the model is created to leverage that against new data that's coming in to predict whatever it is you're trying to leverage the model for. The key thing here is two key things really are that we're writing SQL. So if you are not well-versed in TensorFlow or various other programming languages that are traditionally used for data science type workloads, you can do all of this in native SQL with a few kind of extensions to SQL language. And the other key thing is that it leverages BigQuery processing engine. It doesn't move the data out into any other type of system. So it's not doing like a bulk move of the underlying data to then process in some other processing engine. It all happens natively in BigQuery. And I have an example of this to show you really quickly. I can make my screen bigger. And I'm just gonna actually show you, maybe I won't run all the queries and everything, but I'll show you what it looks like essentially. So if you wanted to create a very simple model, in this case, we are creating a logistic regression. We're just determining whether or not somebody has the propensity to purchase, right? Are they going to actually transact? This is not necessarily a viable model that would be created, but here is what we're defining as the label, so the total of transactions. And the features that we're leveraging are the operating system, if it's a mobile device, what country they're in, and how many times the page was viewed. And from that information, we're trying to determine whether or not somebody is likely to purchase. We're using data from this table from Google Analytics, and we're using data from 2016 August through 2017 June, right? And so I can run this. It takes a little bit of time. It takes several minutes to kind of process through all of this data and create the model ultimately. Now I'm controlling the type of model. There's additional parameters that you can enter here. But once the model is created, you can run queries to actually evaluate the model. So you can evaluate, and this actually should run relatively quickly because I created the model already. But you can get information that evaluates the model, and it gives you accuracy scores, your log loss, like all of this other precision information, so that you have a feeling for whether or not the model itself is accurate. It'll tell you information to, you can get even further information from the model, which I can show you in the UI as well. But then what's great is that in SQL, you can now say, I want to select just the country and whether or not we're predicting somebody is going to purchase in total from the model. And then we're feeding in new data. Now this is data from 2017 July to 2017 August. So we're feeding that into the actual model so that we can predict whether or not somebody's going to purchase based on these features. And so that's pretty cool now. All of that's done in SQL and all of it's done in BigQuery. And actually, because we have this actual data, then additionally, we can actually do a comparison quickly that shows the results from the prediction along with the actual, whether or not they actually purchased. Since the data is from 2017, we know that at this point. So we can see that our model it's pretty close. In the United States, we're off, by 20 or so purchases, but it's pretty close for the rest of them. And so this is all done in SQL. It is all done in BigQuery processing. And I think it's, if we talk about superpowers, I know that this isn't like a traditional data warehousing use case, but doing these types of analyses on data that exists in data warehouses, those are use cases, but most data scientists are pulling all that information out and using other systems to do it. So just a quick rundown of the models that are currently supported today. So you can do different classification, XGBoost, logistic regression I mentioned, k-means clustering, and matrix factorization, which is in beta now. And you can do your more traditional like linear regression as well. And you can import models from import TensorFlow models, XGBoost models, and everything like that. So you have a relatively broad range of things that you can do in BQML, and we're continuing to put out further algorithms all the time. So this list will continue to grow a lot in the future. Really quick, can I have like 5 or 10 more minutes? Is everybody hanging in?
Go for it.
Okay. I see we still have pretty much everybody here, so hopefully you have your beverage of choice and maybe have eaten some pizza or something. So not too much more. I wanted to mention geospatial as well. So BigQuery has now all geospatial data types, so you can have data that store polygon, multi-polygon collection information, point information, and all types of geospatial formats. And also has native support for dozens of different types of geospatial functions. So now you actually have the ability to do these measurements, transformations, and so forth directly in BigQuery, again, in native SQL. There's a geographic visualizer, which I regret I didn't set up to demonstrate, but you have this capability now to start to look at being able to visually represent this geographic information. So typically you might kind of link up with an Esri database or something like that in order to do this type of geospatial functions and geospatial processing. But that can all be done in BigQuery as well. And I'll put Felipe on the spot in a minute. He might have some really good examples of how some customers are using this. The last section, I swear, is about platform interoperability, and I think this is also really important and a huge, huge superpower for BigQuery. Now, BigQuery is part of a very large platform, Google Cloud Platform. We've got tons of different analytic and data processing solutions that are out there, and there's a lot of native integrations that are built between them. But what I think is really like the most powerful thing that we've recently created is the BigQuery Storage API. So I mentioned that BigQuery data is stored in this capacitor format. It's only accessible and read by BigQuery, and I was not entirely truthful in that statement because the BigQuery Storage API now enables you to actually reach into BigQuery storage, sort of like it's any other type of like blob storage for your, more like Hadoop, Spark type of workloads that are outside of BigQuery. So where your data is structured and semi-structured and is stored in BigQuery, and you want to use it in, say, Cloud Data Prop, which is our managed Hadoop, Hive, Spark, and Pig environments, or Cloud Data Flow, which is the unified batch and streaming runner for, why is it escaping me right now? Felipe, I don't know why I can't think of what data flow is the runner for, but if you're there, I'm not on mute. Yeah, Apache Beam, thank you. I lost the words, but yeah, it's our runner for Apache Beam, so you can do both batch and stream processing using Apache Beam. And previously what would happen is when you wanted to operate with BigQuery, you would have to use these connectors that would ultimately dump the data into cloud storage, and then you would leverage it from there, which obviously had some serious performance implications. Now with BigQuery Storage API, you read specific columns, and you can do, low-level filtering and things like that, but it'll read this all in parallel. It enables for you to run high-performance data frames on BigQuery. It essentially creates Avro or Arrow serialization. So Arrow is super optimized, in memory data format. And so you can, like say you're running Spark workloads, you can use your BigQuery data without moving it outside of BigQuery. Of course, it gets moved into Spark or whatever your processing engine, but you don't have to first dump it out to cloud storage, and that's extremely powerful. And it was taking workloads that were taking 30, 40 minutes down to 1 or 2 minutes. So we're talking about huge performance implications here. In addition, we talked a bit about the query federation, so being able to reach out into other systems, reach out into Google Cloud Storage. So you've got, again, all running in BigQuery, all running in GCP, but you've got this capability where maybe you've got a bunch of time series data that's going into Bigtable, and you want to query that alongside of data that's in BigQuery. You can actually federate, have an external table. So you create kind of the structure and the metadata of the table in BigQuery. It looks like a BigQuery table, but actually the data lives in Bigtable. And only when you go to query it does the data actually get temporarily kind of moved into the BigQuery execution space. Of course, with query federation, your query is only going to be as fast as the kind of engine that's performing it and the format that the data is in. So your fastest option is going to have the data materialized in BigQuery, but this is great for some percent of your data where you may not always want to materialize it in BigQuery. So I just had a couple more slides on the storage API, but I really think we kind of hit it there. It does like some key things. I mean, it's very, very fast. We're talking about 500 gig per second. You can do filters on rows and columns. It is immediate, like there's no waiting time for it to, again, export to cloud storage or something like that. And again, like we were looking at previously like 20 megabytes per second. We're talking about 5,000 megabytes per second of data moving, or potentially faster than that. So depending on the use case. So the use cases I kind of already mentioned, there are a lot of third-party BI tools that are leveraging this to speed up processing, and you can use it to create all sorts of custom connectors for any of your workloads that you want to be able to get that type of throughput coming out of BigQuery. So I just have more information for you here. First of all, everything BigQuery can be found in the definitive guide to Google BigQuery that Lakshmanan and Jordan Tigani put out just recently. So it was actually just published, I don't know, maybe like less than 6 months ago. You will see an older version of it. Make sure you get the newer version of it if you're interested in reading it. It has a deep, deep drill down into all of the concepts that we talked about. But also, if you want to learn more about Data Studio on top of BigQuery, you can see Felipe, who's doing a meetup this Friday. So there's a link to it in the slides. Again, another shout out to Felipe's log on the 10 top tips to unleash your BigQuery superpowers. You'll get a little bit of a different kind of perspective on some superpowers in BigQuery, and frankly, Felipe's a lot more fun to read his blogs than to hear me speak. So, and then we've got an official blog and a couple of tools for assessing your data warehouse, or if you do have a data warehouse that you wanted to migrate, we've got a migration offer that you can drill into a little bit more. So with that, a few minutes past time, but that's all I've got for you. So we're open for questions, conversation, discussion. Felipe, if you wanted to, give yourself a little promotion for the meetup that you're doing on Friday, we'll be happy to let you do that as well. If he's still here.
For sure. Of course I'm here. And I've been so inspired by you. So thank you, Jolie. How are you all
So
doing?
yeah, Felipe, no, was just talking about your meetup on Friday. I don't know if you want to give a quick explanation of what you'll be talking about in case anybody.
Yes, I don't know if you want to close for questions first, or how do we? I'm just super excited that I just published a blog post that I would love to show, but I don't want to take off first your stellar time. But on Friday at noon Pacific, I guess that's 1 p.m. Utah, I'm going to be live with Yufeng. He's going to interview me, and we're going to share the best practices to work with Data Studio and BigQuery. So we are going to build together a Data Studio dashboard with the best practices when you're doing this with BigQuery, at least the best practices according to me.
What are the best practices?
That's awesome. Yeah, so we'll post the slides to the Slack channel. I think there's quite a few people here who are using BigQuery and Data Studio, so Felipe's meetup right up your alley.
Awesome.
So yeah, that'd be great. So yeah, terrific job, everybody. Give them a, you can unmute, give them a big round of applause. I'll be clapping along.
I love the order to unmute, yes.
Were there any questions that were in the chat that didn't get answered, or anything that anybody wanted to chat about?
What kind of models are supported in your machine learning?
Let's give a full rundown. I'll actually bring up
Thanks,
our,
Felipe.
did you just put a link in there?
That's cool.
I lost my screen, sorry. Yeah, okay, so that's the blog that you just published. I wasn't sure if you put the link in. So, so the list of all of the models that are currently supported can be found on cloud.google.com, and the reason why I'm not simply answering you is because it changes so quickly that I don't know exactly what is currently available. So let me share my screen, and we can kind of quickly talk about it together. So, so you can see we've got linear and logistic regression. There we go. So linear and logistic regression. So those were kind of the first two that were initially made available. So you can also do a multi-class logistic regression. So if you have multiple results, so non-binary results for your logistic regression. K-means clustering natively is available as well. And then you can build your TensorFlow model. So like it's pretty much wide open for you from a TensorFlow perspective to be able to build your models and be able to import them. So there isn't really like a restriction around what types of models can be done there. Surprisingly, like the matrix refactorization, I feel like was just may not have made it into the docs yet, because I think it was just made publicly available, which is why we don't see it here, as well as XGBoost, which although XGBoost was made available some time ago, so not sure why they're not listed here. But also listed in the slides is everything that is currently available was available at the time of the slide creation.
That's pretty cool.
Yeah, we think so too.
You sort of hit on this a bit in your talk, but can you maybe give us your thoughts on where you think the data lake fits into a world where like a BigQuery does a lot?
Sure. So I think there's, that answer is a little bit multi-dimensional, because there are certainly, I don't want to say like BigQuery is going to be the source of your data lake, because not all data makes sense in BigQuery. However, any data that you are performing like large-scale analytic processing on that's structured or semi-structured that can go into BigQuery, it does make a lot of sense to put it there for that type of active access and to leverage the storage API to use it, because you get a number of various different benefits from doing that. First of all, you get the benefit of not having to duplicate your data and not having to worry about whether or not your data is in sync for those elements of data. And then you have like all of the governance around, BigQuery has really robust capabilities for being able to determine who can see what data, what levels of data. We've got we've got column level access controls and various different ways to do row level access controls, and all of these things can kind of be managed in the BigQuery space, and you kind of inherit a lot of that that comes along with it by having that data in BigQuery. However, the likelihood is that you're going to have a hybrid approach whereby you also are storing a lot of elements of data, or maybe like long tail history and things like that in Google Cloud Storage in some type of optimized format for other types of processing. And storage is cheap in BigQuery. Storage on super compressed data is cheaper in Google Cloud Storage. So if you've got 50 years worth of data and you only really regularly query 10 years of that data, then probably that 40 years worth of data makes more sense in cloud storage. But because Storage API exists, it enables you to take like that data, which you do analyze frequently, and be able to kind of have that be the foundation for that portion of your data lake. Dataproc can very powerfully have the data foundation be BigQuery, GCS, or a combination of those, and has those integrations. So, Dataproc is really great because it does enable you to separate your storage and compute in that sense of like, you don't have to use attached HDFS for those type of Hadoop workloads.
Thanks.
Yeah, and I think Matt might have pinged the chat asking Felipe if you have any further thoughts on that.
Yeah, specifically, I think the question was about streaming and caching from Victor Siu. Victor, maybe you could just chime in, and I don't know if you know anything about this off the top of your head, Julie, or I don't. So.
Yeah. So so if you are like streaming data is going to invalidate caching every time a row shows up in the table, right? Because you're not going to be able to guarantee that the data is the same, and that's essentially why cache gets invalidated. Now, if like you have streaming data, but for whatever reason your source is not active and nothing's streaming in, like your cache, you would be able to have user cache on top of that. But as soon as then your stream starts actually actively inserting data, it's going to invalidate.
Gotcha. Yeah, that's just based off of what you said. That sounded like what would happen. Is just I wasn't sure if there's any sort of like partitioning that would happen that would only check for affected rows and see if any of yours were affected, that kind of thing.
No, it doesn't try to be intelligent around like, oh, you're filtering for so many years ago or something to that effect. Yeah, it doesn't do that. I was pausing for a second thinking like, does the cache recognize partitions if you're looking only at older data, but I believe it does not. Although maybe Felipe can confirm, because it looks like maybe you're saying different in the chat. Will Spanner ever be supported as an external data source for BigQuery? My crystal ball, which is purely speculation based on my own thinking, is that probably it will be, but that's not based on any factual information that I have.
What about federation to other data, other cloud sources like RDS, for example?
I just want to say,
just throwing it out there as a product.
I cannot answer that question, but I can tell you that today Anthos went GA.
Nice.
Yeah, okay. And for Anthos, if anybody isn't familiar with Anthos, it's essentially bringing Google Kubernetes engine to other clouds. So it enables this like hybrid cloud approach to things. Felipe, I don't think you actually got censored. You might have muted yourself. Any other questions? Okay, so hearing no other questions, I guess we can just probably stop the recording and open up for networking.
Cool. I'll stop the recording right now.
Thanks.